Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Vorhies, your host. I'm the Editorial Director with Data Science Central and also Chief Data Scientist for Data Magnum. I'd like to start off our event today by thanking Databricks for sponsoring today's event. Databricks is a longtime supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. Now, past webinars are available on demand at datasciencecentral.com, and if you haven't had the opportunity to view them, I encourage you to take a look. They provide very useful insight into a wide variety of topics of interest to our data science community. Now, today's webinar is entitled Training Your Neural Network, and that'll be presented by Databricks. But before we begin, I'd like to briefly review the format for today's webinar. Today's event will be an hour long. We have one presenter who I'll introduce in just a minute. There'll be 10 to 15 minutes of Q&A following the presentation, and this event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. Now, I'd also like to encourage our attendees to provide questions throughout the presentation. We'll be reviewing and presenting them on your behalf during the Q&A session of today's event. Well, I'm very pleased to introduce today's speaker, Denny Lee with Databricks. Denny is a technical product manager at Databricks. He's a hands-on distributed system and data sciences engineer with extensive experience developing internet-scale infrastructure, data platforms, and predictive analytics systems for both on-prem and cloud environments. He holds a Master's of Biomedical Informatics from Oregon Health and Science University, and has architected and implemented powerful data solutions for enterprise healthcare customers. Hey, Denny, thank you for being with us today. We're looking forward to your presentation. Now, in today's Data Science Central webinar, we'll cover the principles for training your neural network, including activation and loss functions, batch sizes, data normalization, and validation data sets. Now, all these concepts will be brought to life by demonstrating how Databricks simplifies deep learning, letting you quickly access ready-to-use machine learning environments, as well as prepare data and train models faster. Now, after the session, you can request to receive this presentation and the associated notebooks so you can run these samples for yourself. Well, Denny, with that, I'm going to turn it over to you. You can begin just as soon as you're ready to go.
Well, thank you very much. Really appreciate the time for being here. Let's just dive right into it. Today we're going to be talking about training neural networks. A little bit about ourselves, Databricks. So we are here to accelerate innovation by unifying data science, engineering, and business. Our product is the Unified Analytics Platform powered by Apache Spark. Databricks, we were the ones, were founded by the original creators of Apache Spark, and we continue to contribute heavily to the open source community. With that, let's dive right into it. I'm going to skip the about the speaker because Bill has done a wonderful job. So as a quick call out, this is the second part of a three-part deep learning fundamental series. The first, we initially had a session a couple weeks ago, Introduction to Neural Networks. We are going to review some of the key concepts here in case you have not attended that session. This session is training neural networks, and the following session will be applying your convolutional neural network. Okay? From the standpoint of the code base and demos we'll be using, we're going to be making use of Keras with the TensorFlow backend, but as this is a fundamental series, we're still going to be primarily focusing on the concepts. Just to provide, here's a couple of slides just to provide some quick context. The introduction to neural networks, which was a previous session, these were some of the concepts like what is deep learning, understanding the effective activation functions, which we're going to talk about. The current session, which is training neural networks, we're going to be focusing on tuning training algorithms, optimization, including ADAM, and the beginnings of convolutional neural networks. And the upcoming sessions, like I said before, we're going to be applying those neural networks as well. Okay, so diving into it. This is what a convolutional neural network, an example convolutional neural network looks like. This is based off of the code base that you're going to be seeing here, okay? So we're going to showcase that, and excuse me, we're going to showcase that shortly in the session. So we're going to come back to this diagram in a moment, but I just wanted to call that out, okay? All right, so let's talk about tuning training. So in the context of common questions that are asked in terms of like the hyperparameters associated when you're tuning training, questions like with your network, how many layers, how many neurons, what activation functions to use, and then later on with your learning algorithm, what's the best value for learning, how quickly the decay rate, what loss functions should we use. We're going to go into those key concepts, okay? All right, so first things what we want to talk about is more of the context of overfitting and underfitting. So for example, if you've got yourself a graph here, a balanced fit on this graph of data on the x-axis and y-axis of these dots is this nice line right in the middle that basically gives you a generalized model, in this case a linear regression model, but generalized model of the data that's available. If you're going through underfitting, that means you're not really actually designing a model that actually fits the data. So hence the concept of underfitting, okay? Or you might risk the idea of overfitting, which is that you're way too precise. And then the problem with that particular context is that now you don't have a generalized model any longer. You have a model that's very specific to the data that you have. So what we're going to do is we're going to try our best to talk about how do we design this so that we can have balanced models as opposed to an underfitted or overfitted model, okay? And so in general, when you talk about the hyperparameters for your network, the more layers and the number of units in each layer that you have for your neural network, the greater the capacity of your artificial neural network, okay? The risk is that if you're overfitting when your goal is to generalize build a generalized model. So in other words, if you have too many layers or too many units, that's the risk you'll have. You risk overfitting for the scenario that you have. So from a practical perspective, a good starting point is the number of inputs is equal to the dimensions of features. The number of outputs is equal to the number of classes, okay? Start with one hidden layer and 2 times the number of input units. And there's also a good reference here. Now, these may not be as obvious yet, and so we're going to get into some of the context real soon about how this is going to be all applied, okay? All right, so there's also the question of which activation function to use. So we had talked about this in the previous session, but a good summary to call out is this. Basically, a good starting point is ReLU, okay? Note that many neural network samples, like the Keras-MNES, TensorFlow CFAR pruning, they all use ReLU as their primary activation function. Note that each activation function has its own strengths and weaknesses. So a good quote from the CS231N course with Andre Kaparthi is basically use ReLU, start with that, but be careful with your learning rates and monitor that there might be dead units in the network, okay? If you have concerns, give leaky ReLU or max out a try. Don't use sigmoid, try 10H, but 10H is going to be worse than ReLU or max out. That's a quick call out here, okay? All right. So now, as a quick demo, we're going to showcase what we had talked about in the previous session. So I'm going to show that right now, just so to give you the context. So in this example, I'm showing you a quick demo of running the MNIST dataset using Keras-CNN, okay? And so the MNIST dataset, in case you're not familiar with it, is a dataset of handwritten digits, okay, from the U.S. Census Bureau, okay? So 5041. The data, this notebook, by the way, will be available for folks to use, okay, to download and use yourself. But in a nutshell, the data, so you can, in a nutshell, basically the data is a set of numbers that you're going to see like this, okay? So for example, this is me looking at one example of the training data set, and there's a lot of numbers that are representing the handwritten digit, okay? So it's really hard to see that number, but here's, for example, beyond the zeros, you get to see some greater than zero values to represent the handwriting. Okay, Now, if I was to go ahead and show this in 28 by 28 mode, you can see that, okay, it's a little bit easier to see, but if I zoom out, it might be easier to see still. But what we've done is we went ahead and rewritten this, okay, using just in Excel, actually. And actually, you can see a full-size version of it right here. So what we did was basically color-coded it for any value that was greater than 0. And so as you can see, now you have the numeric representation of the number 9 inside the data, the MNIST data set. So this is just one small example here, okay? All right. I'm going to skip past the GPUs, but again, it's in the notebook to call out the fact that using GPUs is actually really powerful, okay? We covered that in the previous session. But saying that, what we've done here is basically showcase the fact that we're going to run this convolutional neural network. This diagram that you see in the notebook here represents the code base that you're going to see here. Again, we're going to talk about more of this in the third section, actually. But for this session, we're going to focus primarily on the optimizers, okay? And so we're going to talk a little bit about that later. And so the call out from the previous session is that if I tried a sigmoid function, the accuracy of how well I could predict the values was at 97.26%, using 10H, 98.77%, but if I use ReLU, now at 99.18%, okay? So in other words, by just simply changing the activation function and doing nothing else to the network, I was actually able to get more precision, more accuracy, excuse me, okay? So this is one of the things we had covered in the previous session, okay? And hopefully that catches up to speed in terms of where we're going to go forward from now. Okay, so back to the slides. So now we want to talk about hyperparameters in terms of what's the best value of the learning rate, how quickly decay the learning rate, momentum, things of that nature. So let's talk about that within the context of training algorithms. We're going to go back to mathematics first, though, in order to be able to talk about this. All right, so a little about cost functions or loss functions, okay? So using a linear regression example, again, just because it's easier to showcase, the cost function, we calculate the cost function such as mean square error or mean absolute error to basically figure out what's the best slope of the line, right? In other words, how to minimize the error between the line and the dots. We're trying to minimize that cost, so that allows us to basically find the best model. Now, this is the context within linear regression, but nevertheless, it's the context basically is to minimize. Hence, it's also why it's also known as a loss function. Okay, so in the case of gradient descent optimization, if we were to take a derivative of that curve, okay, that's what you see on the left side, and on the right side is actually the model that you're seeing. So, for example, as I try to go down to find the lowest, the minimum possible cost function value down the derivative of that slope, then on the right side, I get closer and closer to the best possible model to represent my linear regression. Okay, so as you can see, once that dot gets to the bottom, now the line gets to the point where we think the linear regression model is best represented. Okay, so the problem with a small learning rate is basically this. If your learning rate's too small, what happens is that I keep going, but it'll take a long time to get to the point, to the global minimum, to the bottom of the curve. So this is just a small example of it, but basically because I've made the rate too small, it barely can get actually to the bottom. And so the model I have isn't representative of the actual data that I see here, okay? A little bit of a switch before we talk about larger learning rates. Let's talk about a neuron again, okay, an artificial neural network, okay, a simplified two-layer ANN, excuse me, okay? So what we have here is on the left two circles is 2 input nodes. We have 3 hidden layers and 1 output layer, okay? So what we're going to try to do here is calculate the hidden layer values here, okay? That means the 3 middle ones, okay? So we have an input of 1, okay, which is the value basically that's associated within the input's neurons. We have the weights that are associated, okay, as you can tell, the weights to go from the first input neuron to all three hidden neurons as denoted in black. Okay? You also have the three green values, which are the second input neuron, the bottom input neuron, and their values inputted into the three hidden values, okay? And so as you can tell, basically it is the hidden value, each hidden neuron node, their value is basically calculated by taking the sigmoid in this example, and the sum of the weight times the original value, the input value, okay? And so what we have here calculated is basically 0.8, 0.75, and 0.69 for the hidden values here, for the hidden nodes, excuse me, all right? So now that we start with there, again, we have the hidden there. Now we want to get to the output, all right? So in other words, again, take the inputs from the three hidden layers, multiply that, or each one of them, by the weight, and then you'll finally get the value at the output layer node, okay? So this is basically how an artificial neural network works in terms of the math, basically the summation of the different nodes, okay? Now, a concept that we need to talk about is backpropagation. All right, so backpropagation is basically this context. Originally, the value was 0.75, but we actually know the real value should have been 0.85, not 0.75. Okay, so basically, because of that, we're basically doing a backwards propagation, which is to readjust the weights based on the final value. In other words, between the value we calculated and the final value, so we can make the model more precise. So we're doing backpropagation to make the model more precise. And so it's also known as the backward propagation of errors, as the errors calculated and distributed back through the network of layers. Okay, so what does this have to do with a larger learning rate, right? Because we talked about the smaller learning rate, what it has to do with the larger learning rate? Well, the problem with the larger learning rate basically is this, is that if all the values are positive during backpropagation, the weights will all become positive or negative, creating zigzagging dynamics. And the problem with the zigzag dynamics is basically it will completely pass the minima. So as you can see right here, basically it never got to the bottom of the cost function curve. It literally went ahead and passed it because it was doing these zigzagging dynamics. So that's the problem with a large learning rate. And for in the a notebook that we will be providing you, we're going to show you shortly how that happens, okay, what the final impact is, which ultimately is you have a worst accuracy level and you have a much higher loss because of the fact that you chose either a small learning rate, too small learning because it never gets to the model, or you choose a large learning rate which is completely passes the minima altogether. Okay. All right, and so that's basically the call-out, right? It's too small, it may take too long; too large, it may skip the minima altogether. Okay, so that's the quick call-out there. Now, this invariably leads us to talk about optimization. So let's talk about, which is basically, in other words, when we're doing that backpropagation, the parameters need to be updated, okay? And so when we update this, there's basically several approaches, and we're going to approach basically, talk about stochastic gradient descent, momentum nestroms, and per parameter adaptive learning rate methods. And so for those who you already skipped ahead, typically the ones we're talking about are the per parameter ones now, okay? And so, but we'll give some context on how we got there. And so that's what this next section of slides is going to be talking about. So in the previous slides, when we talked about gradient descent, as you could see, we were basically gently going down the curve in order to get to the minimum. All right. The context of the concern with gradient descent is that it's computed on the full data set. And so in other words, it basically takes the full data set and places it into memory. So this is not really efficient for large-scale models and really large data sets. It often so what you can do instead is use stochastic gradient descent, which allows you to split up the data and then distribute the calculation. It often converges faster but it does because it performs updates more frequently. But due to the frequent updates, this may complicate the convergence to the exact minima. Okay, so that's the concern for stochastic gradient descent. But generally, it works really well. That allows you to take a large data set, distribute that, and find that the minima that you need to find. Okay. So that's so the concern, like we said about the stochastic gradient descent, is that it may complicate the convergence of the exact minima. It's sort of graphed in this. This is a graph that from Annealing's machine learning Coursera course. So the source is right there. But for example, if you are running a stochastic gradient descent, and for example, if you start in the wrong location, you may end up in two completely different locations. Right? You start here, you're down. You start in the middle, completely in the middle, you're actually going toward the right side, and versus if you start a little bit to the left, all of a sudden you're actually more toward the left central side. And so the simple fact that you're just trying to do the gradient descent calculations, the cost function calculations, may result in your models being quite different. And so because of that, that's why it's really important to be able to figure out what is the best way to update the parameters in your model such that you can go to the global exact minima, or the right one in essence, okay? Now, there's another methodology that you can potentially use called momentum or Nesterov accelerated gradient, okay? You can often obtain a faster convergence because by helping the parameter vector build up velocity. So think of it as a ball rolling down the hill. The hill is your cost function curve, and basically as the ball is rolling down, it goes faster and faster and faster, right? So and basically that's why it's called momentum, because it's actually, in essence, they're using the speed of going down the hill to go faster, so you can get you can converge faster to that minimum. All right. Nesterov's, basically, or NAG in this case, is an optimized version of momentum, and in practice typically works better than momentum by itself, okay? But the context basically is that you can go faster, use the speed of the gradient to make the ball roll down the hill faster so you can get to that global minima faster, okay? All right. The potential problem with that approach basically is that you need to anneal the learning rate, okay? And so what that means is basically you need to slow it down, okay? And so remember how in the previous slides we talked about how there's these zigzagging dynamics where you're going to bounce around the cost function curve. Well, in essence, the same context is applied. If I'm going to roll down the hill too quickly, a ball roll, you know how when a ball rolls down a hill too quickly, it'll actually go, it might go past the bottom of the hill and start rolling up the other on the other side. Think of that, except now there's also rocks on that hill, and then the ball will just bounce off from one side to the other side of the hill. Okay, think of it almost like that, as in if it's going too fast, it will bounce around too much. Okay, and then it might miss the bottom of the hill because it's bouncing around too much. And so typically, when you are using these type of optimizations, you might need to apply a decay parameter, okay? So that way you're able to reduce the energy. In other words, i.e. slow the ball down so it'll actually stop at the bottom of the hill, all right? And so note that this is in many of the TensorFlow and Keras optimizers, there is a parameter called decay. Okay, so that allows you to basically, if you feel that it's going too fast, you're able to slow it down so it can actually make itself there, all right? Now, this is actually quite different from the row parameter, okay? So just in case you're looking at it and you see a row parameter, that's actually the exponentially weighted average or the exponentially weighted decays of past gradients, okay? So the best way to think about that is, and so the explanation I have here is like to smooth the descent path trajectory. And so the best way to think about it is more like, think of the hill that you've got here, right? Again, and normally a hill isn't very smooth. What a hill is basically pretty rocky, and it has its own little ups and downs. So it's basically, it has its own up and down motion in the hill itself. It's not some smooth side hill. It's not a smooth curve, right? So what the purpose of row is basically is an attempt for us to go ahead and actually smooth out the hill a bit So that way we can figure out how to get to that bottom of the hill as smoothly as possible, as opposed to as walky as possible. Another way of looking at it is like if you look at the weather or stock trades over time, and throughout the day it jumps up and down a lot. The exponentially weighted average basically smooths out that value, so you can sort of see the stock prices or the weather average or the mean or the whatever value it is over time. So in essence, you're applying that exponentially weighted average. We're going to apply that same context to the learning rate as well. Apply that to the cost function curve itself as well. All right. All right. And so finally, we do need to talk a little bit about per parameter adaptive learning rate methods. So now, prior to this, when we talk about in the context of stochastic gradient descent or talk momentum or even other methods, which we're not going to discuss today, like Jacobian matrices, Hessian matrices, basically they're typically done at the full level, like they're applied globally. And so what we want really is a method to adaptively tune the level of the learning rates at the parameter level, okay? So in other words, you want to basically, each parameter that's applied to the model, you want to be able to go ahead and tune it and apply a slightly different learning rate if so desired, okay? And so popular methods are ADA grad, which improve performance on problems with sparse gradients. It's often used in natural language and computer vision problems. The RMS prop, or root mean square propagation, it maintains that per parameter learning rates. It does really well, actually. And in fact, when you look at the demos we're about to show, you'll see that happening, okay? And then also a more common one that's actually utilized is ADA delta, which is per dimension learning rate method for gradient descent with, and the key aspect here is that it's a minimal computer overhead, requires no manual tuning, and it's actually very robust, okay? And so we're going to talk about how each of these methods, and I'm actually going to show this initially first in a visualization, okay? And so, before I do that, let me talk about which optimizer. And so again, from Andre Kaparthy's CS231N course, in practice, Adam is currently recommended. It's often works slightly better than RMS prop. However, it's often worth trying SGD and SRO momentum as an alternative. So basically, just like the activation functions or anything else when it comes to neural networks, there is current guidance that we're going to rule of thumbs, but there's always, number one, exceptions to the rule. And number two, just as importantly, we have to be up to date on the current research because, for example, one thing I'm not covering in this session is things like, when it comes to activation functions, things like leaky ReLU, or the latest optimizers, which we're not really, which in terms of the research papers, right? The ADA delta, for example, is a paper that was written back in 2012 or 2015. So in other words, we still have active research going on to figure out what are better optimizers right now, okay? But let's sort of see it graphically in action, okay? And so if I'm looking on a loss source contours, this will actually go again so you can sort of see what's going on, right? Basically, if you've got yourself your goal basically is you have the same starting point, but you're trying to get to this, the global minima endpoint. You notice that basically the SGD momentum, the ones in red and ones in green, they're really slow, okay? The red one's actually the slowest of all, okay? And the green one's actually a little also quite slow to get to that endpoint, all right? The problem is that momentum also, the green one, and also the pink one, okay, they really overshoot. They completely go to a different location first before finally getting to the global minimum, okay? And then finally, if you look at ADA grad in blue, the ADA delta in, I guess it's green, and RMS prop in black, they head directly from the starting point to the minima with ADA delta, the greenish one, getting there the fastest, though both the RMS prop and ADA grad are doing a pretty good job catching up as well, okay? So this sort of gives you some context of saying, okay, I've got a cost function. I'm trying to get the fastest to the minima. And right now, in those previous slides, I really only showed just a very simplistic cost function curve, which is basically a linear regression model. When you take into account the fact that a cost function, when you have many nodes in a network, neural network, it's going to be a lot more complicated. And so it's going to start looking closer to this. And so, but it's still, the context is nevertheless the same. You are trying to find a model that has the minimum amount of error going from one point to the next. Okay, so in other words, for example, when I'm doing the mathematics in my neural network, when I'm trying to, for example, do that calculation on the hidden nodes, I'm trying to minimize. I know what the quote unquote the real value is. I know what is being calculated. Can I now adjust the weights so that way the whole network is going to have the least amount of error between what I calculated and what the real value is. Okay, and so because I'm trying to do that, that's where why the cost function is so important, and that's why the optimization is so important to go ahead and figure out how to readjust the calculation of that cost function so we can properly minimize it. Okay. Another way, basically, is if I was looking at the optimization on a SATA point as opposed to surface contours, right? And you'll notice basically how, in the case of SGD, which is in red, it gets stuck at the top. I mean, it just keeps on even right now, it's just bouncing right on the top. Versus if you look at the adaptive ones, basically the yellowish color ADA delta, the blue ADA grad, and the black RMS prop, they basically find the minima and drop down the curve. But what you'll notice here right away is that RMS prop and ADA grad, they all go down the same curve just as quickly, okay, together. ADA delta goes down the fastest, though you notice it's slightly off, slightly different. And so the context here is basically there are times where this is the reason why, yeah, ADA delta is pretty fast, it gets to the point, but you notice that Nesterov, ADA grad, and RMS prop actually follow the same line to get to the minima. So in other words, there's a slight difference in calculations, and you have to be aware of that fact. And in fact, we're going to show a little bit more of that inside the follow-up notebook. Okay. All right. So there's actually a lot more stuff, and so what I've done instead of actually trying to get more of that information in is I've placed links directly to what we've talked about, like learning rate schedules, ADA delta, so things like that. So this is hopefully is a good reference for you to work with. Okay. All right. Good homework, basically. All right. So before we get into the books, let's finally talk about convolutional neural networks at a high level. Okay. From a high level, basically, they're similar to artificial neural networks, but CNNs or CovNets make explicit assumptions that the inputs are images. Okay. So the context basically is that real neural networks don't scale well against images because if you need to go ahead and have a fully connected network, that basically means you're going to have a lot more weight. So for example, if I was to take a image of 200 by 200, 200 pixel width, 200 pixel height, and 3 color channels, now I have 120,000 weights, right? And so this becomes untenable really quickly. And the fact is that if you look at an image, not all neurons need to be connected with each other, okay? So in other words, you need sections of the image to be connected to each other, but you don't need the whole image to be connected, okay? So because of that, CNNs make that assumption that not all the neurons are in a fully connected manner, okay? And so here's the context, basically. So on the left side, this is your regular 3-layer neural network, basically input layer, hidden layer 1, hidden layer 2, and then you have the output layer, okay? That's great. Now, in the case of convolutional neural networks, basically, you do make the assumptions that are basically this. You arrange the neurons in 3 dimensions. You have 3 input results in a 3 output, okay? And so there are inherent presumptions made right away of the system, okay? Because of that, now let's talk about CNNs. The key callouts or the key points of a CNN involves typically some version of convolutions, subsampling or pooling, and a fully connected layer. Okay, and we're going to talk about that right now, and we're also going to show that in the code itself. Okay, so the input, for example, is your 32 pixel by 3 color channel, like the number 9 here, or in this example, like the handwritten digit 3 that you have here, okay? Then when we do a convolution, we're just going to compute that dot product between the weights. Now remember how we talked about before, we're talking about the input and we're talking about the weights. Now we're talking about dot product because it's basically it's matrix algebra calculations that are being placed here, right? And remember we're doing it to a small local region, so we don't have to apply it to the whole thing, okay? So we're using 32 filters, and the output is a 28 by 28 by 32, okay? And we're going to talk about stride, padding, and all these other concepts of filtering actually in the next session, just because that by itself is a lot of information, okay? So, but the context basically is now we have a convolution. So if I had, for example, 8 filters, in this example of the screenshot that you see here, I have 8 filters for the value 3. This is more or less what the convolution would look like, okay? All right. And so then I'm going to pool it, which is basically I'm going to downsample size or a subsampling, okay? And then basically along the spatial dimensions of the width and height. So basically my 28 image just went down to 14 by 14, okay? All right. And so then there's the subsampling. Okay, and then you're fully connected. Now that I've done the convolutions and the pooling together, subsampling together, excuse me, now I can do the fully connected method back together, okay? And so basically, in essence, what the fully connected and the result of the fully connected is that now I just have a 10-class representation. And the reason I have 10 classes is to represent the 10 digits. And so, basically, remember it starts at 0, so that means the 4th dot represents the number 3. So in this case, based on the model, we predict that the handwritten digit that we inputted is 3. Now, not the 9 that you see originally, but the 3 that I placed in the images here, okay? And so actually a very good demo to sort of show this in action is this one here, actually. So I'm going to switch back to the screen here. All right. Okay, perfect. So this is also Andre Comparthy's convolutional net.js MNIST demo. And so what you'll see here, and the link is inside the slides, okay? But the context basically is here's the input that you're coming in, like the 1, 8, 6. And so as each layer of this particular convolution network comes in, then you see what's basically happening. So here's the convolution to the digit 1 to the digit 9 here. Then there's the ReLU, the activation function, okay, that's happening. Then there's the pooling. And so you notice that the pooling or the subsampling is basically shrinking the size of the number here, okay? The physical size, excuse me, of the image, excuse me, sorry. And then again, we do convolution. So now that we've pooled it, we've done another convolution, okay? And then ReLU, pooling, fully connected. But then once we do the fully connected and apply softmax, what you see basically is now as each number comes through, what is the predicted value? So it's predicting, 6, 2, 1, and so forth and so forth. And in fact, actually, the examples of what it's predicted is actually right here. So for example, it predicted the 7, but also there's parts of it that thought it was a 2 or 3. Or for this one, it predicted it was a 1, but then the parts of the network that thought it was a 4 or 6. This one's an 8, but thought it was 3 or 2, so forth and continue, okay? And so that's more or less the context of saying when you have a neural network, it's not super precise, but there are different sections or different neurons that are going to apply different weights that are going to make you go one direction versus the other. But the network as a whole has figured out that what's the value, okay? And so hopefully that gives you some context of when you're playing with it a little bit, as you're going through, what the values sort of look like per se, okay? All right. So then here's the part 2 of this notebook, which you can use. And so if you're not familiar with this is just a quick context. This is a Databricks notebook. I'm running this on a Databricks cluster with GPU, so that way this can be executed pretty quickly. The notebooks will be made available to all attendees, okay? This is the part 2 one, but also the part 1, which focused on activation functions, which we talked about earlier in the session. That one is also going to be made available for everybody to download, okay? And so we're going to go through, specifically in this session, we're going to be focusing on the learning rate and different optimizers, which is what we had talked about for a sizable chunk of today, okay? And so we're going to skip some other sections of the code, so we can focus on those two things specifically, okay? And so we're going to skip past the part where I'm saying here's the numeric representation of the MNIST data set here, okay? But again, you can start looking at it. Remember, this image or this graph, which is also in the slides, is a graphical representation of the CNN we're about to build. So in other words, you'll notice this, okay, you have an input, I have two convolutions, a pooling or subsampling layer, a dropout, fully connected dropout, and finally a softmax to get me to tell me what number it's predicting, okay? So in addition to adding all this additional text, this translates directly to the code you have here, okay? So in other words, convolution layer, convolution, pooling, dropout, flatten, fully connected, dropout, okay? So this code literally step by step you see here is step by step this CNN that you see here, okay? So hopefully that helps give you a little bit of context of what's actually happening, okay? So if I was to run this code, okay, for example, with ADA with different rates, I'm going to just run this one right now. This will take about 2 minutes to run, so I'm going to skip ahead to some of the other ones. But basically, I'm going to try different learning rates. Okay, in other words, remember how learning rates means how fast I can go down that curve or that cost function. Okay. All right. So I actually already graphed it out, but you can run this yourself, and I'm actually running this right now. Like I said, it'll take about 2 minutes. And so basically all I did was I ran this convolutional network. Specifically, I'm using the ReLU activation function, okay? Again, if you're looking for why we chose ReLU, in the part 1 of the notebook, we actually do a comparison between 3 different activation functions, sigmoid, tanh, and ReLU, and basically ReLU won out. So that's why we're using ReLU. And so now, as you can see here, here's the learning rate that I'm going to apply. So I have a learning rate of 1.0, I have a learning rate of 50, for example, or whatever else. So we're going to try different learning rates. And so you'll notice basically here in this graph, this is me taking the data that I've visualized. Okay, so what I did basically, just to give you some context, all I did was take the results that I had from here, I put them inside here, okay? And then I went ahead and create a quick Spark data frame, and I'm just showing it. That's all I'm really doing here, okay? So let's just hide the code back here. And so right now I'm visualizing that data. So at 0.01, we have a modest test loss, but we have a pretty decent point of accuracy, okay, at 0.95, all right? But then at 0.1, now our loss is, in other words, what data we lose or what information we've lost is actually a lot lower, and we're at 0.99, which is pretty good now, right? And then at 1, we're even lower loss and just a tad higher of a learning rate. Actually, it's the highest one you have, actually, if you look at the data itself, actually. Okay, it's still running here, so I'll just go ahead and show you this. There you go. All right, here we go. So basically, at 0.1, it's 98.61%. At 1.0, it's 99.04%. Okay. So, but then I increased the learning rate to 10. Okay. So, wow. Well, then now my loss is going up, and my learning rate, my accuracy is actually going down just a little bit. But I'm not overly out of it yet. Okay. But then, now I went to learning at 50, and you'll notice that the loss is quite extreme. Now we've massively jumped up on my loss, and you're actually just dropped down big time. So I have a 2.3 loss, and I've dropped down to 10% of an accuracy. So in other words, this is pretty crappy here, basically. Okay, and so remember, that goes back to this learning rate's too small. Okay, so if you look at the 0.01 and 0.1 values, okay, the learning rate's too small. Basically, because it's too small, it can't quite get to the bottom of the curve. At 0.1 is doing better than 0.01, but still not better than 1 because we can't get quite to the bottom of the cost function curve, which means we can't get to the label data as fast. Now, of course, these are analogies. This is not what the cost function of a neural network looks like, but this is just an analogy to give you the context here, okay? And then in the case of 10, especially 50, where the learning rate's far too large, this goes back to our concept of the zigzagging dynamics, right? So in other words, because the learning rate's too large, the analogy is then basically as we're going down the cost function curve, we're zigzagging around, and we've completely missed the minima, and we're going above the hill now, okay? And so this is the reason why, you have to test the parameters to figure out how you're going to go test the parameters and record all this information in order to figure out what the right learning rate is, because different optimizers are going to have different learning rates. Okay, and this is actually going to become very apparent in the next next part of this notebook. Excuse me. All right, and so we're almost finished, by the way, just to provide some context. So basically, now what we've done here is basically to speed up the test. I just ran this one. Sorry, I'm just making sure this one's finished. It is, yeah, here we go. 99.26, finished in about 2 minutes. Okay, perfect. So I'm going to, in order to make this run a little faster, I'm doing only one epoch, which is basically one full run of the data set that we have. This is the MNIST data set that we have here, okay? But if I was to go ahead and do a comparison between the different optimizers here, okay, and the different number of epochs that we have, here's the representative graph. And so what you notice is that when I start with only one epoch, both the SGD and Nesterov's optimizers are pretty low, okay? And they're not, I mean, don't forget, this graph is, they're still within the 90% range, okay? So it's not like this is 0 to 100, okay? But basically, we're trying to get as close to the top as we can. And so, over the more epochs we have, the more iterations we have, we will finally get to that, we might finally get to the point where we get to the lowest minimum, okay, and then there was the highest part of this graph that we can. But then if I was to take a look at RMS prop or Atom or ADA delta, boom, right? They're pretty good right from the beginning, even just at one iteration. And you'll notice that basically in this particular example, ADA delta ekes out, just beats Atom and RMS prop, okay? Not by much, but it just ekes out and beats them, okay? And you'll notice that basically when I run the one, just even on one epoch, right? Here's the values, right? The accuracy is 91 for SGD, but for delta is 98.09. And in some cases, you'll notice, like I said, Atom by itself actually was, and our prop at one epoch was actually better right from the get-go. But once we make it about 12, yeah, basically ADA delta was able to eke it out, okay? And so that's an important context also in terms of saying, what is the impact or effect of both the epochs that are being applied, the number of times you're going to go through the full data set, and more importantly, what optimizer you're choosing. And so this is the reason why if you look at the Keras CNN example, which I did link to at the top of the notebook, by the way, okay? Basically, what you'll notice is that the default that it uses, the code base it uses, is basically both Keras, is actually also using the ADA delta example, okay? Excuse me, optimizer, all right? All right, so let's see. All right, back to the slides here. So hopefully that gives you a little context of the importance of learning rates, the importance of optimizers in the impact of your convolutional neural networks. I just wanted to give you some call out to some very good additional references that'll help you do some good homework on this stuff. Also wanted to thank Tomek Drabus, Brooke Weneg, Timothy Hunter, and Cyrielle Simeon for their amazing help to put together the session. And finally, I wanted to call out that there's 2 additional sessions. There is one, which is the Applying Your Convolutional Neural Network, which is basically the 3rd session of this deep learning fundamental series that you were talking about. Remember, we're number 2, and this is the 3rd one. And also, there's a Data Science Central awesome session on the 31st of October, the state of the art of deep learning on Apache Spark, just in case you're interested. And with that, I shall hand it back off to Bill.
Well, Denny, thanks very much. That was a terrific presentation, and we'll get started with today's Q&A session. I want to thank the audience for their participation. I had a lot of questions that have come in, and we'll do our best to get through all of them in the time remaining. During this session, I'll leave up this screen with contact information for Denny if you'd like to get a hold of them following today's webinar. So let's get started. Denny, the audience has observed a lot of what you focused on was how to get to the most accurate answer as quickly as possible, but they're also wondering about overfitting. What happens? How do I tell if I've got too much accuracy?
So what it comes down to is when you have too much accuracy is basically, this is back to the context of saying when you have how typically in the code, and we talked about this in the first session, so I apologize for not providing enough context in this session, but typically you have a training data set, a test data set, and a validation data set, okay, when you're working with your data. So when you run your training data set, you basically build up the model, right, that you're trying to create. And then you run your test and validation data sets against that model to determine what's going on. So what typically happens is that when you're running your tests, whether it's test or validation, what will happen is that the data, the precision of the model, the accuracy or the loss is going to actually completely go out of bounds. Right? In other words, if you were to reapply that same training data set, it's going to have very high accuracy. But you apply any other data set, the accuracy drops, right? And that's more or less a very telltale sign that what you have here is you've got a model that's overfitting. In other words, you've built a model that's really well designed for your training data set, but it's not designed to be generally used for anything. So whether it's a handwritten data set or you're looking at MRIs or anything that you want to apply your neural network to, basically the simple fact that your test and validation data sets end up resulting in a massive drop in accuracy, while your training data set has a very high level of accuracy, that's what will result in you. Basically, that's the telltale sign of overfitting.
Well, Denny, thank you very much for that clarification. Now, the audience is wondering about something very basic, and that is, why are deep networks better than shallow ones? For example, early on, one of our audience members observed that your model would be best if it were 4 layers deep by 4 neurons wide. And I suppose the extension of that question is, well, how do we tell the best number of hidden layers that we should be using?
Okay, and so we sort of covered some of those key concepts basically in the session, but allow me to sort of rehash and be more precise in my answer here. So the context of deep networks versus shallow networks is that when you have a deeper network, you have a greater capacity for more neurons in the network to help calculate the inputs based on the weights. So it can actually have handle more parameters, more features, more components in the network overall. In other words, that's the context of greater capacity. So in other words, back to that specific example of 4 layers deep and 4 neurons, that could potentially be a good starting point. But by the same token, you do need to take into account of what is your input and what is your output. Okay, so if your input is an image, basically with all the features that you have, the inputs is actually probably going to be a lot more than 4, right? And so it's going to be a lot more information. So, in one of the previous slides, we sort of called out the fact that the hidden layers should actually be is basically a ratio to the input layers you have. And then also, what is the purpose of your output? So in the case of our output, we know we have 10 classes because we have 10 digits to represent. So again, now your network itself, the number of neurons that you have to apply, the number of layers deep are going to be different in this situation versus in some other situation. Okay, so that's why there isn't a straight up answer to say whether you should go ahead and do of the number. What it comes down to is understanding those key tenets, number one, and number two, knowing, trying out and testing and retesting. So one of the things that you'll see, and I sort of covered in the notebook that you saw where I basically was recording lots of information, okay? That's what you're going to have to keep doing, right? In other words, you have to have a mechanism just to constantly test, try out different architectures, which we'll cover in the next session, try out different layers, different learning rates, all these different things. And so you start basically typically with what people have done in the past. So you have you have like a foundation to work with, but then you keep on testing with different hyperparameters, different learning rates, different architectures to get to the final result that you're looking for, right? And so that's why, you know, I'd love to be able to give you a straight up answer saying, yes, here's what you have to start with, but there really isn't that answer. It's just simply saying that, yeah, if you have deep networks, that's great because it allows you to basically have a greater capacity, but the problem with deep networks also is that you do run the risk of overfitting.
Okay. Oh, thank you for that clarification. Now, I know you spent a lot of time talking about stochastic gradient descent and gradient descent. The audience is asking if you would please give a brief review of those two, and particularly, is one of them necessarily better than the other? And at the same time, the audience has also asked, is SGD, stochastic gradient descent, the same as SGB, or are they different?
Oh, okay. Actually, sorry, Bill. For the last part, SG, I might have heard that incorrectly. Is SGD different from
SGB is in boy?
Oh, SGB. Okay, I could be completely incorrect on this one, but I'm not familiar with SGB. I'm presuming it would be stochastic gradient boost, but right now, really, we're definitely focusing more on SGD, which is stochastic gradient descent. Okay. And so now that in terms of that context of stochastic gradient descent basically is great, and it's the model that we begin with in order to basically go down that cost function curve to get to the minimum amount of error. And so again, if I was to use the simplified linear regression idea, the minimum amount of error between the line and the dots on the XY axis, the lowest we can possibly get is the best model that represents the data. So in the case of gradient descent, the call out is that you have to take this information and you need to prop it into memory fully in order for you to calculate it. Okay? So while that's awesome, that's not good for larger data sets. So that's why you'll see stochastic gradient descent applied, because that allows us to distribute the gradient descent calculation onto a distributed node. Because when you have larger amounts of data, at some point you're going to have to break the context of being able to put all the data in memory. And so, for example, that's part of the reason why you'll see a lot of the machine learning functions within Apache Spark itself, within this Databricks notebook that I showed you. The reason that we have that is basically it's because it allows us to take that calculation and distribute it across multiple nodes very easily. And so that's why you notice that we start with SGD. But then again, when it comes to neural networks, you notice that the optimizer starts with SGD, but we quickly go into these other optimizers. And right now, as noted, right now the current research says 88 delta, or at least per adaptive methods. I'm pretty sure in a few months from now, there might be something else.
Well, Denny, before we go, we have to let you answer this question, and that is, folks are really interested to know, where can they see session 1, and can they get the notebooks for session 1?
Oh, no problem. Yes, absolutely. So we will make sure, as when we send, we'll work together with Data Science Central to send everything prepackaged together. So in other words, both the session, this session, the previous session, and for that matter, the future session, and all the associated notebooks are available for you to download. They will work on, these notebooks work perfectly fine on Databricks Community Edition, so you can get the free one, try it out, use it yourself. Obviously, if you want to use the regular edition Databricks, by all means, but it'll work on the free one as well. So.
Well, Denny, thank you. Those were some great answers to some very good questions. And for those of you that asked questions today that weren't answered, we'll be sending all the unanswered questions to Denny and the Databricks team so they can follow up with you after today's webinar. I have just a few quick announcements. If you'd please mark your calendars for October 16th. That's our next DSC webinar, which is dashboard design with the user in mind. Now, also remember that today's taping will be available for on-demand viewing later today and you can find that on the home page of Data Science Central in the Webinar tab located at the top of the page. Well, this brings today's webinar to a close. I'd like to thank our audience for their attendance and thoughtful questions. A special thanks again to Databricks for their sponsorship, and particularly our speaker today, Denny Lee, for his insight into today's topics. This is Bill Vorhies. I'm very pleased to have been your host for today's event. I look forward to seeing you all again on October 16th. Have a great day.